So I want to talk a little bit about how do we make these FinFETs device, and it's actually quite fascinating, and I'll try to describe more than one ways to do it. So one way to do it is make these fins in a subtractive manner. So you can have your substrate, and you have your hard mask, and you have photoresist, and you have that anti-reflective coating, which is called as bark, as we talked about in last week. And then you can etch that pattern into your silicon, and you get these silicon fins. You can fill it up with an oxide, so you fill it up with this oxide layer, and then you can essentially CMP it off, so it planarizes. And then you can remove that this blue nitride layer on the top, and then you can etch back this oxide to reveal your fin. And this thickness of this height of your fin in this case is determined by how deep you etch back. So your height is determined by how deep you etch back how deep you recess that oxide back to reveal your fin. There could be another way to do it, and so we talked about that we use double patterning. So we can have this amorphous silicon hard mask. We pattern that, and that becomes we have this amorphous silicon mandrel, and we pattern that using our photoresist. Then we deposit a spacer around it. You can etch back that top of the spacer, so it leaves these side walls. And then you remove your mandrel, and you're left with these spacers, which are twice the density, and then you can etch them back into this nitride. And then you can recess that nitride into your silicon if you want, or you cannot if you can skip that step. But essentially you fill it up with oxide, and then you're left with this mold. And the thing why I'm calling it a replacement fin flow is you etch that nitride off, and you create this mold. So you create this mold material which has this oxide which is making this mold, and then you can fill it up or do epitaxy of your silicon to make this fin. And again, you do your epitaxy. You can actually do epitaxy of any material you want. So you can, if you want to integrate other materials on your silicon wafer, this is a perfect way to do it. You make a small high aspect ratio mold, and then you can grow any material into it. It will create defects over here, but those defects would be trapped within this mold, and then your top surface would be defect free. And then you can recess this back again to the height you want, and you get these fins. So this is one way where you want to integrate, say, germanium or 3,5 materials onto same substrate. So you can create your silicon fins first, and then you can create this mold, and you can do your epitaxy of that other material into this small trench, and then you can reveal them back together. So now you have two fins of two different materials on a same substrate. So this is a powerful way of making these fins as well. Again, I'm going a little fast, but there are videos which talk about this part in more detail on the site. So you can, this part, that's why I'm going a little fast. Another way to make these fins is you make them on a SOI substrate. And as I'll just show to you, actually a lot of the initial work on making these fins was done on these SOI substrates. So you use a double patterning. So you have a mandrel, you have these spacers, and then you etch them to define these fins. The advantage of doing this way is that in your earlier process, your height of the fin was defined by how deep you do that recess etch. But in this case, you start with a fixed thickness of silicon, and you etch that fixed thickness. So your height of your fin is essentially predetermined by how thick that SOI layer to start with was. So this is, again, it has that advantage that your height of your fin is determined by your thickness of your SOI layer instead of being defined by your etch process, which can introduce variability. And a lot of early work on FinFETs was all done on SOI FinFETs, because the reason is that it's easier to define these fins, and it's very hard to do a STI process in a university lab. I don't know any university, at least in US, which can do that other kind of process, but it's easy to define, much easier to define fins this way. So here's some pictures. So again, this is showing a double patterning step. You start with a mandrel, you make these spacers. You can go further, you can make them quadruple, you can go crazy, make it quintuple, and we can keep on increasing these fin density. And there's, here's some pictures showing if you have one of that spacer, then you can do again double patterning to double that pitch density. You can do a quadruple patterning to make it 4 times. And Sam talked about it last week. He sees no problem in keep on doing this and defining, doubling the pitch as many times as he wants. So here are some pictures of different fins. So this is showing fat fin, thin fins. So knowing whatever we have learned about spacer defined, assuming that these fins are defined using a spacer based lithography or a say a SADP or a self-align double patterning process, which of these do you think are actually possible, or which of these are could be actual pictures of devices? Right now these are the cartoons. Can this be done? Probably not, right? It looks too perfect. You can't do lithography this way. The thing is, if we rule out any of them, then we rule out a lot of them. Whenever we do a spacer-based lithography, right, if you have a roughness in one edge, your spacer is essentially conformal to that edge. So you don't, your roughness between this surface and that other surface are always correlated. So you can't have something which goes like this or something which goes like this, because this edge and this edge are always correlated. So if you patterned a mandrel, you patterned essentially this layer, and then you defined a spacer on top of it. So let's go back here, right? So suppose you had a roughness in this layer, your mandrel, and it was rough. When you deposit the spacer conformally around it, this outer surface, outer edge of your spacer would have the same roughness, right? So your roughness between your inside and outside layer are always correlated. So this is not possible, this is not possible, this is not possible, this is not possible. So we can rule these out, and we can, if you use a spacer-based lithography, you cannot get patterns like that. You will always get patterns which have your roughness between this inner and outer layer always be correlated to each other. And that's in fact very good, because that means that no matter how rough our fin is, the width of this fin would always remain constant, or it won't vary as much as compared to, say, if you use some other process like 2 lithography steps, or LE kind of a process. So you'll get a lot of variation in your fin width. And as I discussed, our fin width is one of the key parameters for determining your threshold voltage and your short channel effects. So this spacer-based approach of doing lithography is really awesome for making patterning these fins, because you get a constant width. So here is comparing this CD, or this by CD in this case meaning the width, that is the critical dimension, and you see that if you use say any other process, you get a much larger variation, versus if you use a spacer lithography, you get a much tighter distribution of this width of your fin device. So this is the preferred approach that people use to pattern these fins. So once you have patterned the fins, I want to talk about a few challenges that are very specific to the 3D nature of this FinFET device. And there are many challenges, but I want to talk for the benefit of time. I want to focus on 4 of these main challenges. So the first challenge I want to talk about is fin collapse. These fins, I want to make them taller and thinner, but that's only can happen in an ideal world. What happens when you make these fins taller and thinner is you get these capillary forces. So whenever you're doing a wet process or you're doing any kind of process which wets the surface of these fins, you get these capillary forces, and these capillary forces are proportional to the 4th power of your height. It's inversely proportional to the 3rd power of your width, in this case the width of your fin, and it's also proportional, inversely proportional to the distance between these fins. So these things are, a lot of these things are essentially controlled by design rules, how much is the distance between these fins, how thin you can make them. But if you make them thinner, you essentially increase this capillary force. If you make, again, you space them closer, you increase it, but not as much, because it's one is proportional to, inversely proportional to the 3rd power, the other one is inversely proportional to the 1st power. And when you make them taller, again, you make the things work. So if you make these tall and thin fins, they collapse, and this is showing some pictures of them collapsing with each other, or away from each other. So this is a big problem in making your fins taller and thinner, and also making them vertical. Another thing which again comes into picture because you have this 3D device, is you get all these corner effects. So remember a planar device, how nice and in a single plane it was, and when you go to a fin, you get all these edges and you get these corners. And as you might remember, whenever you have a corner and you have an equipotential surface, you always get higher electric fields at your corners. If you have a knife, you will always get the highest electric field at the tip of the knife, or if you have a needle, you always get the spark from that needle at the very tip of that needle. So the same thing happens here, and you get a high electric field at your corners if you have a conformal gate wrapping around it. So your corner of your fin always turns on faster. So this is plotting the current density, and you can see that say in this case it's plotted for a voltage near to your threshold voltage, and you can see both in your bulk and your SOI FinFETs you get this current conduction happening through your corners when they should be really turned off. So this kind of degrades your overall leakage, because at this voltage they should be really off, but because of these corner effects they are now turned on. So this we have worked so hard to make this device, but because of this corner effects it's all ruined. So how do we get around these corner effects? So one way to get around the corner effect is get rid of the corners, right? So it's very simple. So you make it a round fin. Apparently this is not very hard to do. If you take a fin like that and anneal it in a hydrogen environment, it will turn into something like this. So you can or you can taper it like this, as we saw in that Intel cross section. So both are ways of getting rid of these corner effects. The downside of this is if you have fin like this, you have multiple widths. So you have one width here, you have another width here, you have another width here. Similarly, you have one width here, you have a smaller width over there. So as we discussed our our device electrostatic is very dependent on the width. So that being a smaller width here, this would have better electrostatic, a larger width here, this would have poorer electrostatic. So you get this multiple width problem, so you kind of get into that same space where you have these different devices turning on at different voltages. Another problem that you get is these planes are off axis, so these are not at any particular crystalline axis, and as I'll just describe you, that degrades your transistor mobility. Another way to get rid of that corner is essentially put a thick dielectric on the top. So I'll use this edge and this edge, and I won't use that top edge at all. So I'll put a thick oxide here. So I use essentially this and this, but I don't use that. So that's another way to get rid of your corner effect. So another challenge, which is again very peculiar to this 3D nature of your fin device, is your spacer stringers. And what I mean by that is, we talked in the class last Monday that we have these spacers between our gate and our source drain, which allowed you to do all that implant engineering, do your extension implants, and it also helps you to separate your source drain contact from your gate contact. And these spacers are essentially defined by side walls. So where you have a side wall, you will form a spacer. The problem with this FinFET device is that you have two of these side walls. You have a side wall over here, which is the side wall you want to keep your spacer on, but you have this extra side wall over here, which is really, your fin has two side walls. So if you do a conformal deposition, you'll get a spacer around here which you really want to keep, but you'll also get a spacer around here which you really don't want. So this is illustrated more clearly in these cartoons here. So if you do a spacer process, you'll get a spacer, which is, so this is taking a cut along this axis, so you'll get a spacer here, and then if you take a cut along your fin, you'll get a spacer along here as well. And there's no analogy of this in the 2D world. So all these complexities comes just because of this thing being 3D. And to realize it, again, you need to look at multiple cross sections and get your head around, that this is okay. Having this extra fin emerging from the surface of the earth really screws up my process or complicates my process. So what they do is, you have this, they make this gate fin, they make this gate taller, so you get a spacer which is like this over here, which is tall, and you also get these spacer which is on my fin, and then I can do a very sophisticated etch such that I etch this part out and I remove this spacer because I don't want it, but I still keep my spacer on my gate, on my between my gate and source drain. So again, it works against my argument that I really want to make these fins taller, but then I can't remove this stringer around them. So this is again challenge number 3. Let's look at another challenge, which is making this junction. So I talked about, we can, junction engineering kind of becomes easy when you go to a FinFET, because you get rid of your halo implants, you get rid of your body doping, but you still need to dope this source and drain, right? So you need to dope them, and since it's a 3D device, you want to dope this whole fin which is hanging out with a uniform doping. And if you do an implant from the top, you will dope the top surface, but you won't dope the center of the fin. So this is, if you do an implant process just from the top, you'll end up doping these surfaces which are facing the top, but you'll not dope the center as well. So what you need is really all these implants happening at different angles. And the problem with that is, since these fins are 3D and they're hanging out of the surface, when you want to implant your P fins, you want to probably protect your fins, which are your NMOS, and you have this photoresist which will have a certain thickness too, and that photoresist at least has to be thick enough to cover these fins, right? Otherwise it won't protect these fins. So whenever you do that, you are restricted by the amount of tilt that you can get into this window, because you have this very narrow window into which you want to do your implant. So again, your forming your junction becomes much more complex when you have this 3D device. So one way to get around is that, use a doping process which is conformal. So use a plasma instead of ion implant process, which is less directional to do your implant, or you can make these junctions by doing epitaxial growth of your source drain. So remember that picture you were asking, what was that other picture? So that was that epitaxy, and it looks like this diamond when it grows around this fin, and that's one way to get around this junction problem. But all these problems arise because you have this 3D nature of this of your fin, and that's why it's so hard to make this device. So